Hello, good day. We're now in the moment strength as a function of LP. So actually, if you happen to see the videos, the recent videos that I uploaded from YouTube by Dr. Muhammad, it was already discussed this moment strength as a function of LB. But we'll try to pahapyaw lang guro nga discussion, and we'll try to answer the examples. Also, the example is already discussed by that YouTube video. So, kindly I study na lang po, no? So, the moment length of compact shapes is a function of the unbraced length LB, defined as distance between points of lateral support or bracing. Here, we indicate points of lateral support with X. Say, we have this cross-section, then at certain distance, naa siya ay lateral support. So, from that support to bracing or lateral support, that is LB. Like, for example, this one, this is a simply supported beam. So, iyahang LB or the unbraced length is from the left support, the pin connected support to the ruler. But kung naa kay bracing at a certain distance, meaning ang LB nimo is from the left support to that bracing, that is LB. The nominal moment versus the LB. We have this table in figure, na table, a graph, figure 5.13. So you have this, the x-axis is the unbraced length or the LB, and the y-axis is the moment, We have this M sub R and M sub P. Sa x-axis nimo na kay no stability, you have the inelastic lateral torsion buckling, the L sub P, that is between the L sub P and L sub R. And L sub R, beyond this L sub R, is the elastic lateral torsion buckling. We have these conditions, if L sub B or the unbraced length is less than or equal to L sub P, the beam is considered, we have this L sub P. So from this, from the very left, no instability to L sub P. If your L sub B is less than L sub P, the beam is considered to have full lateral support, and the nominal moment is equal to your plastic moment. Meaning, ang pasabot nimo dire, this is, ang pasabot ni ana, ang pasabot ni ana is kani nga portion dire, kana siya is no instability, meaning ginegate nimo ang duha ka argument nga negative, meaning that is stable, So in this portion, ang imong member or section nimo is stable, meaning pag apply sa load, moabot siya sa yield strength nimo, moabot pagid siya sa beyond sa yield strength nimo. So that is your plastic moment, moabot sa iyahang plastic moment. So very stable ang section nga applying sa loads, mo yield ang section. After that, maabot siya sa iyahang plastic moment. So this section, your M sub N is therefore equal to your nominal moment is equal to your M sub P. If your unbraced length or your L sub B is between this range, L sub P and L sub R, so naa ka diri sa inelastic region, the strength is based on the inelastic lateral torsion buckling. So you will have your moment that is between this M sub R and M sub P, If the lateral if the unbraced length L sub B is greater than L sub R, the strength is based on the elastic lateral torsional buckling. So, meaning, nara siya diri dapit. So, what is elastic? Wala siya kaabot sa proportional limit. Nibakol na siya. Wala pagi siya ni yield. Nibakol na siya. Meaning, unstable ang imuhang member section. So, kindly watch the videos in the YouTube sa kato akong gi-post because iyang gi-explain dito very detailed nga pagka-explain. So, you can refer to the video to better understand this topic, no, in part 2, that is part 2 of his video. So sa in the elastic lateral torsion buckling strength, so this portion kaning portion kana siya, meaning elastic, wala siya kaabot sa iyang yield strength. The AISC equation F2-3 gives nominal moment strength as M sub n, your nominal moment, is equal to the F sub CR. F sub CR is the elastic buckling stress times the elastic section modulus. That is less than the plastic moment. Wala siya kaabot sa yield strength sa steel. Wala siya kaabot sa plastic moment. So, therefore, you have to use this F sub CR, which is the elastic buckling stress. This F sub CR can be solved using this equation. The C sub B, pi squared E over L sub B, then brace length times RTS squared. Square root of 1 plus 0.078. The J, this is the shear moment of inertia divided by the elastic section modulus times H sub O. H sub O, this is the distance between the flange centroids, which is equal to D minus T sub F times the quantity L sub B over RTS squared. This J is what you've learned in your strength of materials. So, J is the polar moment of inertia. No? Yeah, C sub B is the factor to account for the non-uniform bending within the unbraced length L sub B. R sub T squared. This is not squared, no? I think this is dili ni siya squared, no? This is RT. R sub TS is equal to square root of I sub Y CW SX. CW, this is the warping coefficient. This is can be seen in the table, no? Later mag-example ta. Also, the example is also presented or kanang gipakita sa video by Dr. Muhammad. So, kindly see it. Then C is 1.04 doubly symmetric eye shapes. Then, or for channels, that is equal to H sub 0 over 2 square root of IY over CW. Where H sub 0 is equal to distance between the flange centroids T minus T sub F. If the moment when lateral torsional buckling occurs is greater than the moment corresponding to first yield, the strength is based on the inelastic behavior. The moment corresponding to first yield is corresponding to if the moment when the lateral torsional buckling occurs is greater than the moment corresponding to first yield. First yield is the M sub R. The strength is based on the inelastic behavior. The moment corresponding to first yield, no? The corresponding to first yield, that is 30% less to account for the effect of residual stress. So M sub r is equal to 0.7 times the yield strength times the elastic section modulus. The first yield is equal to 30% less sa yield strength, no? True yield strength sa steel times the elastic section modulus. That is M sub r, which is can be seen in this graph. Now, this is the first yield. So, as shown in figure 5.13, the boundary between elastic and inelastic, so in figure 15, behavior will be for an brace length of L sub r, which is the value of the L sub b obtained from AISC equation F2-4 when F sub CR is set equal to 0.7 Fy with C sub b 1.0. The following equation results. So L sub CR is equal to this formula, no? Very kuan na siya. Complicated formula. Tagas na kayo. 1.95 RTS times E over 0.7 Fy because the MR, the LR, which is kaning nga condition, no? The first yield is equal to this formula. Yes, times E over 0.7 Fy square root of the polar moment of inertia J times C. C is 1.0 for doubly symmetric eye shapes, and if channels, kani siya nga equation. Okay. This formula over the section modulus, elastic section modulus times H sub 0 plus square root of squared, no? This one squared plus 6.76 times 0.7 Fy over elastic modulus of elasticity times, squared, no? That is the boundary for elastic lateral torsion, no? As with columns, dirita sa inelastic lateral torsional buckling. As with columns, inelastic buckling of beams is more complicated than elastic buckling, and empirical formulas are often used. For inelastic lateral torsional buckling, that is between this range, no? If the unbraced length is between this range LP and L sub R, L sub P and L sub R, your nominal moment is equal to CB, C sub B times the quantity M sub P minus this M sub P, this is the plastic moment minus the M sub P minus 0.7 FYSX times this ratio LB minus LP over LR minus LP, which is less than the plastic moment because naapa man ka sa inelastic region, no? So your moment actually is below, less than the plastic moment, but greater than this first yield moment, where the 0.7 Fy times this elastic section modulus term is the yield moment adjusted for residual stress, no? 30% residual stress. And L sub P from AISC equation F2-5 is equal to, so L sub P, this L sub P here, the boundary, no, between the no instability and inelastic lateral torsional buckling is equal to 1.76 times Ry square root of E over Fy. Alright. Summary for the nominal flexural strength for compact I and C-shaped sections for L sub B less than L sub P, meaning nakakaabot siya sa plastic moment or diri siya nga region, this region here, no? the no instability. So meaning stable ang imuhang section or steel. Your moment, nominal moment is therefore equal to your plastic moment. Nakaabot siya sa plastic region, no? So for L sub P, or your unbraced length is between this range, L sub R and L sub P, your nominal moment is C sub B times this formula, which is discussed earlier, kani siya, di ba? For inelastic lateral torsional buckling. And for L sub B, which is greater than L sub R, this is for elastic uh, torsional buckling. So, yung L sub B is greater than L sub R, meaning dili stable. Wala pag siya kaabot sa first yield ni, kung ano siya, ni buckle na siya. So, your moment, nominal moment is equal to this critical buckling stress, F sub CR, times the elastic section modulus, which is still no less than M sub P. No? Kaya naman siya diri. In this region. No? L sub B is greater than L sub R. Meaning, L sub B, taas ang unbraced length, no? Than L sub R. Taas na kay unbraced length. Meaning, dili stable ang member. Where the F sub CR, the critical buckling stress, is equal to C sub B pi squared E over L sub B. Yes, this is discussed earlier, di ba? This is just a summary of what was discussed. No? So, C sub B pi squared E over LB over RT squared. T squared. Square root of 1 plus 0.07. Polar moment of inertia C over SX LB squared over RT squared. So, we have this example.